Hello, my name is Francis Kinder, and today we're going to be teaching about Gaussian elimination. So goals for today are to teach what Gaussian elimination is, to teach matrix row operations and what they are, and to teach why Gaussian elimination is useful. And today also happens to be Casual Friday, so casually dressed it is. By the end of this lesson on Gaussian elimination, you should know how to solve a system of equations using Gaussian elimination. You should know how to perform the different matrix row operations. And finally, you should recognize when a matrix is in row echelon form. And before we get started, just some background information. You must be able to do basic addition, subtraction, multiplication, and division to be able to do the stuff performed in this video. And it would also be beneficial if you know how substitution works. Let's begin. Gaussian elimination uses augmented matrices. Well, what is an augmented matrix? An augmented matrix is a matrix that is made up from a system of equations. Each row represents an equation, and each column represents a variable. So, for a real quick example, we have our first equation, 4x plus 7y plus 11z equals 22. Our second equation is 28x plus 34y plus 13z equals 78. And for our third and final equation, 72x plus 66y plus 49z equals 94. And then that becomes the matrix 4, 7, 11, 22, 28, 34, 13, 78, 72, 66, 49, 94. And as you can see, each column represents a variable, and each row represents an equation. And this dotted line right here sometimes appears in dotted matrices, sometimes it doesn't. It depends on which book you have, and just that column in the end represents the solution to the equations that you have. So Gaussian elimination was created by Carl Friedrich Gauss, and a solved augmented matrix looks something along the lines of, like, I don't know, 1, 4, 8, 27, 0, 1, 3, 12, 0, 0, 1, 8. And this is called row echelon form. The goal is to solve for one variable, like right here, and then substitute it into another equation where the unknown variable is multiplied by 1 and the solved variable isn't. You then use basic algebra to solve for the unknown variable. So we take our solved variable, like z, and plug it into the equation up there. We'd multiply 3 times 8 equals 24. And then, well, we'd subtract 24 from 12 using basic algebra, and we'd find that 1 equals negative 12. And then we'd repeat the process again for here with negative 12 times 4 and 8 times 8. And then we'd solve for this variable. The important part of Gaussian elimination is that there is a pattern of diagonal ones starting from the top leftmost entry and going down one row and right one column for every subsequent entry, and that beneath the ones are only zeros. So as we can see from the previous not example, but slide, we have diagonal ones going from the top to the bottom, going down one and right one for every entry, and underneath those ones we have only zeros. So we know this is in row echelon form. So to go from our original matrix that looks like this with all of the numbers filled in, to our matrix that looks like this with the diagonal ones in the zeros, we have to use matrix row operations. Now, matrix operations are functions that we can use to manipulate matrices, and there are a total of 3 of them. First one is we can switch any 2 rows, and that is denoted as R1 double-headed arrow R2, and that just means R1 swaps with row 2. Our second one is we can multiply a row by a scalar, and that is denoted as XR1 becomes R1. So some number multiplied by R1 becomes the new R1. And finally, we can add any 2 rows together, denoted as R1 plus R2 becomes R1. So one row plus another row becomes this new row. So now I'm going to use this matrix, and I'm going to demonstrate all 3 of the matrix row operations individually. So our original matrix was 4, 7, 11, 22, row 2, 28, 34, 13, 78, and row 3 was 72, 66, 49, and 94. And so, first off, I decided to swap rows 1 with row 3. Well, row 1 becomes row 3, and row 3 becomes row 1. So the first row is now 72, 66, 49, 94. The second row stays the same as nothing happened to it, so it's 28, 34, 13, 78. And the third and final row is 4, 7, 11, 22. Now, next I decided to take 4 times row 2 and make it the new row 2. So the first row stays the same as nothing happened to it, so it's still 4, 7, 11, 22. third row stayed the same as nothing happened to it. So it's 72, 66, 49, 94. And then for the second row, we just take 4 times every individual number in this one, and it becomes new row 2. So 4 times 28, 112. 4 times 34 is 136. 4 times 13 is 52. And 4 times 78 is 312. Now finally, I decided to add row 2 to row 3 and make that the new row 3. So row 1, that stays the same. It is now 4, 7, 11, 22. Row 2 stays the same. That's 28, 34, 13, 78. Now row 3 becomes row 3 plus row 2. So 72 plus 28, that's 100. 66 and 34, that's 100. 49 and 13 is 62. And 94 and 78 is 172. So now I'm going to use Gaussian elimination to solve the system of equations that is 4x plus 7y plus 11z equals 22, 28x plus 34y plus 13z equals 78, and 72x plus 66y plus 49z equals 94. And I'm going to time-lapse that now. So it turns out my whiteboard does not have enough space for me to show all of the work for this, but we're going to discuss what I have so far. So first we turn the system of equations into an augmented matrix. So the first equation becomes row 1, 4, 7, 11, 22. The second equation becomes row 2, 28, 34, 13, 78. The third equation becomes row 3, 72, 66, 49, 94. Now the first matrix row operation I perform is R3 minus 18R1 becomes new R3. So rows 1 and 2 stay the same, which are 4, 7, 11, 22, 28, 34, 13, 78. But now row 3 is 22, or 72 minus 18 times 4 is 72. So 72 minus 72 is 0, and then repeat for all of these terms, which becomes negative 60, negative 149, negative 302. And then we did row 2 minus 7 row 1 to become new row 2. So row 1 stayed the same, 4, 7, 11, 22. Row 2 is now 0, negative 15, negative 64, negative 76, and row 3 is still 0, negative 60, negative 149, negative 302. And as you can see, I start building my 2 zeros because this is eventually going to be a 1, and that's one of the cases for reduced row echelon form or Gaussian elimination. Now next I did row 3 minus 4 row 2 becomes new row 3. So rows 1 and 2 stay the same. So 4, 7, 11, 22, 0, negative 15, negative 64, negative 76. And row 3 now reads 0, 0, 172. And also this one, so this 0 is also where it's supposed to be because this is going to be 1, this is going to be 1, and then this is going to be 1 eventually. So now I took row 1 minus row 2 becomes new row 1. So row 1 now reads 4, 22, 75, 98. And this is because 7 minus negative 15 is 7 plus 15, this is 22. 11 minus negative 64, or 11 plus 64 is 75. And 22 minus negative 76, or 22 plus 76 is 98. And then row 2 is still 0, negative 15, negative 64, negative 76. And row 3 is still 0, 0, 172. Now we took 2 times row 3 plus row 2 becomes the new row 2. So row 1 still reads 4, 22, 75, 98. Row 2 now reads 0, negative 15, 150, negative 72, and then 150 is just 2 times 107 minus 64. And then our third row is still 0, 0, 107, 2. And now we took row 1 plus 3 times row 3 to get new row 1. So we get 4, 22, 396, 104. And then row 2 is 0, negative 15, 150, negative 72. And row 3 is still 0, 0, 172. I did this step because since our first number is 4, I want to make everything as easily divisible by 4. And so 396 and 104 are easily divisible. 22 is not, but at this point it really doesn't matter. I couldn't do anything about it. And so then we just took 1/4 of row 1 equals new row 1. I multiplied row 1 by a scalar of 0.25 or 1/4 to get the new row 1. So now 4 divided by 4 is 1. 22 divided by 4 is 5.5. 396 divided by 4 is 99, and 104 divided by 4 is 26. Row 2 is still 0, negative 15, 150, negative 72, and row 3 is still 0, 0, 172. Okay, so we finished the example, and we're going to continue where we left off. So this is the last thing of the previous video segment, and so the next step I did, I took negative 1/15 of row 2 became new row 2 because this number right here is negative 15, and to make that a 1, we just divide by negative 15. And so row 1 was still 1, 5.5, 99, 26, and then row 2 now became 0, 1, negative 10, 72 fifteenths. And row 3 is 0, 0, 172. And next step was to get this last one entry. So I just divided by 107 of row 3 became new row 3. So row 1 is 1, 5.5, 99, 26. Row 2 is 0, 1, negative 10, 72 fifteenths. And row 3 became 0, 0, 1, and then 1 or 2 over 107 or 1 over 53.5. And this is our final matrix. Like, it's not solved yet, but we're getting there. So this right here represents our z. So z, 1z equals 1 over 53, or 1 over 53.5, which is approximately 0.019. And so to find y, we take z and we plug it in for the next equation, or next row up. And so we have 1y minus 10z equals 72 fifteenths. We substitute in for z, so y minus 10 times 1 over 53.5 equals 72 fifteenths. Y minus 10 53 halves equals 72 fifteenths. Y equals, then we just add both sides, y equals 72 fifteenths plus 10 53 and a halves. Well, we have to make like fractions, so y, well, multiply by 53 and a half, multiply by 15. So y equals 3,852 802nd halves plus 150 800-second halves. So y equals 4,002 802 halves, and that is approximately 4.678. Finally, we have to find for x, or our top row. So we have 1x plus 5.5y equals 99z equals, or 1x plus 5.5y plus 99z equals 26. Okay, we substitute our y and our z values in. So x plus 5.5 times 4,002 802 halves plus 99 times 153 and a half, 1 over 53 and a half equals 26. So we get x plus 22,011 over 802 halves plus 99 53 and a halves equals 26. Cross multiply by, or multiply by 15 to get like denominator, so we can add fractions. So x plus 22,011 802 halves plus 1,485 802 halves equals 26. And then I added the fractions and then subtracted them. So x equals 26 minus 23,496 802 halves. And so to subtract a fraction, we have to get same denominator. So we multiply 26 by 802.5 over 802.5, and we get x equals 20,865 over 802 halves minus 23,496 over 802.5 halves, or 802 halves. And that gives us a value of negative 2,631 802 halves, which is approximately negative 3.279. So we found the solution to our equation, or system of equations, with x equaling negative 2,631 over 802.5, y equaling 4,002 over 802.5, and z equaling 1 over 53.5. But how do we check our answers? Well, we can do it one of two ways. We can substitute our values back into all of our equations. Now, why do we do all? Because, as you see here, we can have, for values x, y, and z, we could have 1, 1, and 1, because 4 plus 7 is 11, plus 11 does indeed equal 22. However, if we plug the same values of x, y, and z into our third equation, for example, 72 plus 66 plus 49 does not equal 94. Or we can use it, check our answer by using Gauss-Jordan elimination, which is an extension of Gaussian elimination. So for substitution, it was really quite simple. It was just a matter of plugging all of your x, y, and z values in properly, multiplying, make sure you added correctly, and if they added up. So for our first one, we had 4 times negative 2,631, 802 and a halves, plus 7 times 4,002 over 802.5, plus 1153.5 halves or whatever, equals 22. When you multiply that out, you get negative 10,524 802.5s plus 28,014 802.5s over 165 802.5s equals 22. You add that all together, you get 17,655 over 802.5 equals 22. And when you divide this out, it does equal 22. So for this instance, it is correct. So for our second equation, we took 28 times negative 631 over 802.5 plus 34 times 4,002 over 802.5 plus 13 over, or times 1 over 53.5, and that gives us values of negative 73,668 over 802.5, 136,068 over 802.5, plus 109 over 802.5. It gives us a total value of 62,595 over 802.5. And if you divide that, it gives you 78. 78 does equal 78, so this one is true. So for our third and final equation, we had 72 times negative 2,631 over 802.5 plus 66 times 4,002 over 802.5 plus 49 times 1 over 53.5, and it gives you values of negative 189,432 over 802.5 plus 264,000 over 264,132 over 802.5 plus 735 over 802.5 equals 94. So when we add that all together, we have 75,435 over 802.5 equals 94. And when you divide this in your calculator, you do get that 94 equals 94. So our solutions are indeed x equals negative 2,631 over 802.5, y equals 4,002 over 802.5, and z equals 1 over 53.5. Now that we have covered substitution, what about Gauss-Jordan elimination? Well, Gauss-Jordan elimination is an extension of Gaussian elimination that completely solves a matrix and does not have to use substitution to find your solutions. It just solves for the variables outright. It uses all of the same methods we used before to get a matrix that looks like this, that has 1s in the diagonals and 0s everywhere else except for the rightmost column, which is what the solutions are. And this is called reduced row echelon form. Luckily for us, we have a calculator function that can do it, but I'm not going to show an example of this. So how did I check my solution? Well, I brought up my TI-84 calculator, I selected my matrix, I created a matrix, I went back to the matrix panel and selected the math function, and then I scrolled down until I got the function RREF, open parentheses, which is reduced row echelon form, and then I selected my matrix that I wanted it to solve, which was, in our case, the 3x4 matrix, like 7, 4, 11, 22, and then the next two columns, and then I just mashed enter, and then it gave an output of, well, the first one, x equals approximately negative 3.279, y was approximately 4.987, and z was approximately 0.019. And if we remember from before, that's exactly. So what are some real-world applications of Gaussian elimination? Well, Gaussian elimination is used in the fingerprint image enhancement so that if you took a picture of a specific fingerprint, it zooms it in, and so you can see the fingerprint a lot more clearly. It's also used for scheduling algorithms like making a class schedule or a work schedule. And another use is channel decoding algorithms. These are just a few, but it's used in almost every field, practically everywhere. So what have we learned today? Well, to start off, we learned that Gaussian elimination is useful for solving systems of equations. We also learned that solving these problems by hand is tedious, long, and insanity-inducing. And we also learned that Gaussian elimination is used a lot in the science field for various different things. Now, if you didn't quite grasp how to do the reduced row echelon form, I will be attaching a PowerPoint to this video for better guidance.